All right, we're back. We are on page 4 of notes 2 of Calc C, and we're gonna do one more of these by making our own table and going. Honestly, you're just gonna keep doing that forever. So like I'm saying that we're gonna do one more before we get specific, but like once we get specific, we're just gonna do a lot more of them. So this is the process. You find derivatives, you evaluate them at the center. The thing you're gonna screw up is the center. If you're anything like everyone I've ever taught, that'll be the thing you forget. But when you forget it, your approximations are so far off that like you couldn't reasonably think that you had done it right. So you do get like a hint at least that maybe something isn't going well in that process. So let's see if we can do it. So we have our function is natural log of x. So that's the function that we're dealing with. And then what we're going to do, so we can't center this at 0 because the natural log of 0 doesn't exist. The derivative natural log is 1 over x. At 0, that doesn't exist. So we can't center it at 0. So instead, we're going to center it at x equals 1. You could actually center it anywhere in the domain. Usually you don't even pick. But if you are picking, you usually pick something that's easy to evaluate the derivatives of. 1 is usually a good choice. And so because of the center being at 1, we're going to end up with the quantity x minus 1 raised to powers, right? So we think that the nth term is going to look like it's the nth derivative evaluated at the center, so at 1, and then it'll be x minus the center to the n, and then over n factorial. That's what we think is going to happen. I mean, it's going to happen. I keep saying think, but so let's find some derivatives. So the original function is the 0th derivative. Now, it's better, well, easier. I'll do it here. So the derivative of natural log is 1 over x, but it's easier to deal with all of these if you make it like x to the negative first, because then you can just keep power ruling your way to the derivatives. So negative x to the negative second, 2x to the negative third, negative 6x to the negative fourth, 24x to the negative fifth, and then negative 120x to the negative 6. You might recognize those coefficients, right? We had like 1, so if I were going to fill them in, there's a 1 here, a 1 here, right? So it was 1, 1, why are you scrolling? 1, 1, 2, 6, 24, 120. You might recognize those as factorials, right? So this is 0 factorial, actually. 1 factorial, 2 factorial, 5 factorial. So the factorials have shown up here, which is pretty interesting. And let's see, like, if it has some bearing on what ends up happening. So the natural log of 1, so everything's at 1. Keep that in mind. I don't know what color I'm using for that. So 1. So the natural log of 1 is 0. And then we're going to get 1 minus 1, 2 minus 6, 24, and then minus 120. All right. So, but we know that those are like the factorials. So really, I might use the factorial versions. Maybe not. I don't know. Let's just start writing it. So p of x. Ooh, somehow I deleted something automatically. P of x is, so it's going to be 0, and then the quantity x minus 1 to the 0 over 0 factorial, but those are all 1, so we're not going to do them. Plus 1, the quantity x minus 1 to the first over 1 factorial. I'm not going to write it, but it's there. Minus 1 x minus 1 squared over 2 factorial, plus 2 x minus 1 cubed over 3 factorial, minus, this is a long one, minus 6x minus 1 to the fourth over 4 factorial, plus 24x minus 1 to the fifth over 5 factorial. Not really fitting this. Let me see. If I got rid of the 0, I would fit better. Just gonna like crush some things together here. This is what I spend a lot of time doing this when I'm writing notes. It's like I don't plan. The iPad has really instilled in me the bad habit of like, you don't need to plan ahead because you just pick it up and move it. All right, and then minus 120 quantity x minus 1 to the 6th over 6 factorial. Good grief. All right. So what does this clean up to? This actually cleans up a lot because, so first of all, I mean, the first thing is just gone. Then I like to leave the parentheses around it, and I like to write to the first. You don't really need to do that. So I am going to like simplify this a little bit in a way that I don't ordinarily, but only because this one's kind of famous. So 1 over 2 factorial is just 1/2. 2 over 3 factorial, so 2 is 2 factorial, not that that matters. 2 factorial over 3 factorial is actually just 1 over 3. So the 2 factorial, mostly it's that you can rewrite 3 factorial as 2 factorial times 3, and then the factorials cancel. You're just left with 3. So here it's going to be plus x minus 1 cubed over 3. Then minus, okay, so same sort of thing is happening here. 6 is 3 factorial, and this is 3 factorial times 4. So the 3 factorials cancel, and you're just left with minus the quantity x minus 1 to the 4th over 4. And I think you kind of see how this is going to go, and you can keep working it out if you're not positive, but I'm pretty confident. You got to do a lot of like pattern recognition in Calc 2. And so I'm pretty confident that this is it. So let's, should we do something on the calculator to see if this is right? I guess so. Let's see. I'm gonna do a weird thing actually. I'm gonna ask the calculator to find this. So the way I'm gonna do that is I'm gonna press menu, then go to option 4 for calculus, then press up to get to the bottom of the list. And then I wanna go to series, and I want a Taylor polynomial, right? So I'm just gonna get Taylor. So I want the Taylor polynomial for the natural log of x. The variable is x. I want to center it. No, I want the 6th degree, and then I want to center it at 1. It has an optional center. So let me press enter here. And you can see it's writing it the way that we wrote it. So this is exactly the same as what we wrote. So if I had said I wanted to center it at 2, it's going to be all quantity x minus 2's, but you'll see the coefficients change. And the denominators have changed. If I want to center it at 3, it'll be all quantity x minus 3's, but again, things are changing. So at 1, so 1 is a really good choice because the natural log of 1 is 0. So you don't get like a natural log to lead off, which is a part of the reason you choose it. So we get this. Let's compare. So the domain of natural log is x is greater than 0, which means our polynomial has a domain of all reals. So like there's definitely something that we're gonna have to think about. Like where is it? Wow, okay, here we go. Where is it good, right? So I don't think I actually stored, well, all right, so natural log of x. And then I'm just gonna type Taylor, I'll do it again, Taylor, natural log of x, comma x. I want 6th degree, and I want you to center it at 1, and it gives us this. So look on that interval there. It's like really, really good, kind of between like 0 and 2, it looks like very good between 0 and 2. Then it gets worse. So this is not the best. What if I did like a 20th degree polynomial, right? So that it's the function, comma, the variable, comma, the degree polynomial you want, and then the center that you want. So by default, the center tries to be 0, which won't work on this. So I'm gonna go to a 20th degree polynomial. And you can see it's better. What if we do like 50th? So a 50th is really good between what looks to be -1 and about 2. Let me trace. So I'm gonna trace to 2. So it's really good from, not -1, from 0 to 2. Looks like it's really good. And then after that, seems like things get insane. I'm bouncing between the functions, and you can see at 2, really close. Actually, the polynomial has a maximum at 2. I don't think I was anticipating that. But if you go a little over, now it's starting to be worse. Over more, it's even worse. And then finally, it's like, it's just going to keep getting worse. So it's good on some interval. And that's going to be called the interval of convergence, which is sort of like the domain, but not exactly the same. It's the values you're allowed to plug in if you're going to approximate something. but like you could plug in anything. It's just that, you know, if it's not between 0 and 2 for this particular example, you're not getting a valid approximation of any sort. Like no one would try to defend it. So what we've got so far is this. So it's a big deal, I would say. It's going to stay with you all year. So Taylor polynomial at A. The thing you're going to forget is the x minus a's. I see that a lot. I think you just get so excited. You found the derivatives, you evaluated them, things are looking great, and you go to write your polynomial, and oops, you forgot x minus a to the n. So memorize that. You got, if you don't know it, like you basically can't do the problems. You definitely can't do them in the speedy time that you need to be able to do them. So you have to have that memorized. So immediately memorize that. I will see you in the next video, and we're just going to keep going. So see you there.